So this and the next couple of lectures we look at transient analysis of amplifiers. When we started this course, for the first 3 chapters we had looked at DC analysis. Then in chapter 6 we looked at basically a frequency analysis, a small signal sinusoidal steady state frequency analysis. Then in chapter 9 we have been looking at op-amp configurations and looking at DC and frequency response characteristics. So now let us briefly look at transient responses of amplifiers when the inputs applied are small or large. So by transient we mean the response in the time domain as opposed to either DC or frequency domain responses. And we'll start our discussion with the simplest possible circuit, our common source amplifier, and we'll assume a large load capacitor, and we'll assume that it is so large that we can ignore all the MOSFET capacitances, so that the circuit has effectively only one capacitor. If the MOSFET capacitances are not small, then we actually need to include an RG, a gate resistance, and I am asking why it is important to include. You think about it. For us, because we are assuming that the MOSFET capacitances can be neglected, we will not include RG also in our discussions. We will assume these numerical values for our discussions: a VDD of 3 volts, a CL of 1 nanofarad, which is a large capacitor compared to usual MOSFET capacitances, the usual threshold voltages, lambdas, mu Cox W by L will assume the same for both transistors, equal to 50 milliamp per volt squared. What this will do is, this will make the NMOS and PMOS basically symmetric in all respects. And we'll assume a DC gate voltage for the PMOS to be 2.4 volts. For the NMOS 0.6 volts. So both of them have a gate through source of 0.6 volts and therefore an overdrive of 0.2 volts. And then on top of the DC, for the at the input of the PMOS, we'll apply some transient voltage. Then with these numbers we'll get a drain current of 1 milliamp, a transconductance of the PMOS to be 10 milliamp per volt. You can check all this. And the RO, the output resistance, RO and parallel ROP equal to 10 kilo ohms. So the gain of the common source amplifier being minus GMP RO will be 10 milli times 10 kilo equal to minus 100. Also, because these transistors are completely symmetric and because their lambdas are equal, if we include the lambdas in the DC analysis, we'll find that the DC output voltage will be 1.5 volts because of complete symmetry. So we'll assume that the DC output voltage is this much. As we've discussed before, this is really not predictable, but we need some value to do transient analysis, kind of to get a sense of transient analysis. So we'll assume that the DC voltage is 1.5 volts. All right. So with that, let us look at a few different cases. First qualitatively, and then we look at quantitatively. So we say we'll apply a unit step at the input of the PMOS on top of the DC of 1 millivolt. So very small step at the input of the amplifier, and let's qualitatively see what this will do. So as Vin, so the total Vin will be 2.401 volts. That slight increase in the gate voltage of the PMOS will cause a decrease in the drain current of the PMOS because the source gate voltage is smaller. If the drain current of the PMOS decreases, the total output voltage will also decrease. All right. Okay, just give me 1 second. I forgot to do this. Okay. And as a result, VO will decrease by some magnitude when V in is increased by a small magnitude. But we are saying that the input is changing instantaneously. This is a unit step voltage. So the input is changed suddenly by 1 millivolt. The output will not change suddenly because there is a capacitor connected here. So the output will take us some time to reach its final value until the capacitor voltage changes over a period of time. Now let's ask two questions. What will be the shape of this VOT as it changes from its initial value to the final value, and what will be its final value? All right, so let's think about both these questions. Now we say that we have only one energy storage element in the circuit, and because there is only one energy storage element, we expect that the mathematical form of VOT will be exponential. All right, we say, then I'm asking, will it? So we'll come back to this. For now, let us assume that it will be exponential. What will be the final value of VOT? That will be the final DC value when the capacitor has finally charged fully. So then for the final DC analysis, we can ignore CO, and then we have the input voltage as the output voltage is the initial value minus A0 times V1, where V1 is the magnitude of the input step we have applied. So this is V1 of the input step, which we've said is 1 millivolt. So for a 1 millivolt change in the input voltage, the output would change by 1 millivolt times the gain, which is minus 100. So the output would be 1.5 minus A0 into V1, which is 100 into 1 millivolt, which will be 1.4 volts. So the output would go from 1.5 volts to 1.4 volts. And we are saying it is exponential. We'll come back to this when we do the quantitative analysis. Okay. Actually, I'm answering this question. So as long as this input is small, it is 1 millivolt, then the circuit will behave linearly, and if the circuit behaves linearly, then the mathematical form of VO will be exponential. All right, let's see what happens if the input voltage is not small. So that is the next case. So we're saying the input step now is 0.2 volts, so 200 millivolts, which is a large step if you think about it, because 200 millivolts times a gain of 100 will give an output change of 220 volts, which is very large, right? Okay, so we are saying let us analyze for a step of 0.2 volts. So now the input voltage is 2.4 plus 0.2 into the unit step function. So it is 2.6 volts for t greater than 0. So as soon the unit step causes a sudden change in the input voltage becomes 2.6 volts for t greater than 0. We are ignoring all the capacitances of MP. Therefore, a sudden change in the input gate voltage would change a sudden change in its current. And with 2.6 volts as the input, the gate source voltage of MP is how much? 3 minus 2.6, 0.4. The threshold voltage is 0.4. So MP will carry no current for t greater than 0. All right. What will be the final DC state? So of course, what happens to VO? Let's think about the final DC state and come back to the shape of VO. So finally, because MP is off and the Mn has a gate voltage, so Mn is on but carries no current. So the final DC output voltage will be 0. Initially, for t less than 0, it was 1.5 volts. So the output would go from 1.5 to 0 because the capacitor has to discharge from 1.5 to 0. Now the question is, will VOT vary exponentially with time when this happens? right? What is the answer? Let's think about the circuit at t equal to 0 plus to answer that question. What happens at t equal to 0 plus? The input voltage has become 2.6 volts as we just saw. The output voltage is still 1.5 volts because the capacitor voltage will not change instantaneously. Then what about the currents? MP is off. MP has turned off because the gate source voltage is equal to the threshold voltage. The drain current of Mn is still 1 milliampere. Why? Because the output voltage is 1.5 volts. So Mn is in saturation, and it is in saturation, and so it carries a 1 milliamp current. So what happens to this 1 milliamp? This 1 milliamp discharges Cl, right? So the current flows from Cl into Mn to discharge the capacitor. Now, what is the shape of this discharge? As long as Mn stays in saturation, which it will until VO reaches 0.2 volts. So from 1.5 to 0.2 volts, Mn will stay in saturation. It will carry a constant current of 1 milliamp, and so what will be the shape of VO as a function of time? It will vary linearly with time because the capacitor is discharging via a constant current source. All right. Also, what this is telling us is that when we apply a large input step to this circuit, because MP turns off, the rate of change of the output voltage will remain constant because it is determined by the saturation current of Mn, which is fixed to be 1 milliampere. We'll come back to this point in just a few slides. Alright, now let's apply a large negative step, so minus 0.2. So the step is minus 0.2 volts. So at the input we had 2.4, we are saying we'll have minus 0.2. So the gate voltage of MP instantaneously at t equal to 0 will become 2.2 volts. Alright, so this is a large gate source voltage, and so this is gate source voltage is now 0.8 volts. The Mn has a gate source voltage of 0.6 volts. So the saturation drain current of MP is larger. Therefore, in the final DC state, MP has to go into triode. Alright, so if MP is in triode, the output voltage will be close to 3 volts. It will not be 3, but it will be close to 3 because MP is in triode, Mn will stay in saturation. Alright, once again we ask the question, will VO rise? Okay, so VO is rising from 1.5 volts to close to 3 volts. Will the rise be exponential or linear? Let us look. Let us think about this. So again we look at the circuit at t equal to 0 plus just after Vin has switched from 2.4 to 2.2 volts. So at that moment in time, let us look at the voltages. So what are the voltages and currents? Vin is 2.2. So this is 2.2. The output stays at 1.5 because of the capacitor. If this is 1.5, this is 2.2, this is 0.6. Both transistors are in saturation because this is 1.5. Now let us find the saturation drain currents for both the transistors. For the PMOS, for the NMOS, it is the same. 1 milliamp because the gate source voltage has not changed, so it is 1 milliamp. For the PMOS, the gate source voltage is higher. It was 2.4, now it's 2.2. So this of course is a 3 minus 2.2 is will give us a larger drain current. So we have a 4 milliamp drain current for the PMOS, 1 milliamp for the NMOS. So there is a difference of 3 milliamps. The 3 milliamp charges the capacitor. So the 3 milliamp flows through the capacitor and charges it towards 3 volts or close to 3 volts. Now what will be the shape? As long as MP stays in saturation, It will stay in saturation till 2.2, so 2.6 volts. So 1.5 to 2.6 volts as VO changes, the current in MP will be constant, and that 3 means that 4 minus 1, 3, a constant current will flow through CL and it will charge the capacitor linearly with time. Alright, after that it will be a somewhat complicated equation, because then one has to write the equation for MP in triode. You have, I assume that you've done this in the digital circuits course for an inverter where both the gates are shorted together. So you've seen these analyses before. So this is in fact a revision for you. Okay, one more thing we observe is that when the input step is negative, alright, so from 2.4 we made it 2.2, or we could have made it 2.3 or 2.5, and depending on the size of the step, so that this voltage is 2.3 or 2.2 or 2.1, the saturation drain current of MP will vary. For us it is 4 milliamps. If the input changes, this will change. Therefore, the current charging CL will change, and the magnitude of the rate of change of the voltage VO will change as the magnitude of the input step changes. Alright, this is an observation. Again, we'll come back to this at a later point in time. Okay. Now, let us talk about how do we kind of characterize transient performance. There are many different metrics of characterizing transient performance. We look at two. One is called a settling time. The settling time, you must know, is a time that the output takes to reach within a certain percent of the final value. Alright, sometimes settling time is defined as 1% of the final value, sometimes 0.1%. It varies. The percentage chosen depends on the application. So generally speaking, you will see a number of 1% or 5% or 0.1%. But there are some applications, for example, if one is using this amplifier in a 14-bit A to D converter, then the percentage would have to be less than 0.005. So it will have to be 0.005%. Alright, it's a very small value. It comes from 2 raised to, so some whatever VDD divided by 2 raised to 15. Alright, so that's a very small number. So that's one measure. The other measure is what is called the slew rate, which is the fastest rate of change of the output voltage. And so again, we'll define slew rate in a couple of minutes. Let us first do a quantitative analysis of the same circuit. If the input is small, so if the input is small, we can draw the small signal equivalent circuit and solve it, assuming that everything stays linear. So we draw this circuit, we include the capacitor, and we do Laplace, so we do 1 over SCL for the capacitor, and we derive the transfer function, which is this. It's all straightforward. Now we say with this transfer function, if the input is a voltage step, V1 times a unit step function, then the Laplace transform is V1 over S, and then we can write VO as the transfer function times V1 over S, and then okay, so I'm defining GMP RO as A0 and ROCL as tau. Then if we take partial fractions and do inverse Laplace transform, we'll get the familiar expression. So the output voltage is equal to the final value of the output voltage, A0 V1 into 1 minus e raised to minus t by tau. This is the change in the output voltage. So I am representing the change as a small v subscript O, subscript small o. So this is a change. The total output voltage, which is small v subscript capital O, is a DC voltage plus the change in the voltage. So that is this. So this is 1.5 volts plus all of this, when the input is whatever, some DC plus a unit step. All right. So this shows that the output changes exponentially with time if the magnitudes of V1 are small. Alright, now let's look at one more thing. So this is our output voltage expression. If we take the derivative of this dV dt and find the slope, then the slope is equal to A0 V1, the tau comes out, A0 V1 by tau e raised to minus t by tau. Now this expression has an important property that as the input step magnitude increases, the slope of the output voltage dVo dt increases proportionately with the input step. Alright, this is a property of linearity. When circuits are linear, if the input is increased by a certain magnitude, then the output, or basically everything else in the circuit, also increases by that same magnitude. So that is linearity. Alright, Razavi calls this linear settling. So under small signal conditions, the settling is linear, meaning that the slope is linearly proportional to V1. One has to be very careful while thinking about linearity here. Sometimes, not often, students get confused. Linearity does not mean a linear variation with respect to time. All right, exponential variations with time actually are characteristics of linear circuits. All right, it's a slightly tricky statement, but please recognize it. Linearity refers to currents and voltages varying linearly with other currents and voltages in the circuit. All right, with respect to time, in linear circuits, variations are exponential. All right. Now let's look at also the current flowing in CL in this circuit. Again, the small signal circuit. So the current flowing in CL, of course, is IC, which is C dV dt. CL times dVo dt. We just found dVo dt we found. So we say CL dVo dt, CL times this same thing. So what this is telling us is that the current in the capacitor also increases linearly as V1 increases. Alright, and this is again a property of linear circuits. So to re-emphasize, for small changes in the input voltage V1, dVo dt and the capacitor current increase proportionately with that small change. If V1 is larger, IC is larger. Alright, that is what I want to say. V1 is larger, IC is larger when circuits behave linearly. Alright, what happens if V1 is large? Alright, for large signals, if V1 is no longer small. Alright, so we say it is increased to a large amount. So if V1 is increased to a large amount, then MP will conduct less and less. And eventually, if V1 is large enough, in our case, if V1 is greater than 0.2 volt, greater than or equal to 0.2 volts, then MP turns off, as we just saw. Alright, and then because this is increasing, VO is going to decrease, and VO is going to discharge, CL is going to discharge through MN. And MN has a constant saturation current, as we just saw a few minutes ago. Therefore, once V1 is large enough, let us say greater than or equal to 0.2 volts for our circuit, whatever the magnitude of V1, the current flowing in CL will be constant. It will not increase linearly with V1 when V1 is large. Alright, so that is the difference between small signals and large signals. For large signals, the current charging or discharging CL becomes a constant. It does not depend on the magnitude of the input step. This is the largest current that can exist in this circuit to charge I'm sorry, to discharge the capacitor, and this is called the slew rate. The slew rate is the largest possible dVO dt for a given circuit. Alright, dVO dt max is defined as the slew rate. Alright, for our circuit, the negative slew rate. So a circuit always has a positive and negative slew rate. A positive slew rate is for the voltage increasing with time. A negative slew rate is for the output voltage decreasing with time. For our circuit, for the output voltage decreasing with time, the slew rate, the dVO dt max, is equal to the saturation current of the NMOS divided by CL. Alright, the positive and negative slew rates of a circuit are not necessarily equal. Some circuits they are equal. In our circuit they are not equal. So you think about why they are not equal by just kind of revising the last few slides. Alright, with this let us do some simulations to kind of just get a pictorial view of what we just discussed. Okay, so I have the same circuit that we discussed, that is here, there is an Mn and an MP, and the lengths are such that the current is 1 milliamp, the CL is 1 nano. I have also added a linearized version of this circuit, so this one I have also added, so you can compare the linearized output of the circuit versus the actual output of the circuit, and we are applying an input step at the gate of the PMOS, and I'm going to do these various combinations of input voltages and look at the output. So right now there is an input step of -1 millivolt, and let us see what the output. So we look at the output from the actual circuit and the output from the linearized circuit. Alright, and we'll compare them both. So let us see what they look like. Alright, so the blue and the blue is the actual, the red is the linearized, and we see that for a 1 millivolt input step, I'm sorry, -1 millivolt, because this is minus, the output voltage is increasing with time. So it's going to about 1.6 volts from 1.5 volts, and the actual and the linearized are practically the same. Right, so that is a problem because the input step is small. Let us make it -10 millivolts and run it again. So slight difference, but still basically the same. So here both of them are overlapping with each other completely. Now let us apply -100 millivolts, so that is 0.1 volt, and now the time required is small. So let us run it now. All right, what happened? The red one is the linear one, the blue is the actual one. So what we are seeing is that first of all, the blue one is basically a straight line here, and then of course it is saturating at 3 volts, well 2.9 volts. What is happening? When the input step is negative, the PMOS conducts more current and eventually it goes into triode. So if the final voltage is 2.9 volts or so, the PMOS has gone into triode. During the transient, the PMOS conducts more current, therefore the rate at which the output rises is more than what is predicted by the linear model, because the linear model assumes the same current that was flowing for an input of 2.4 volts. Now with -100 milli, the input voltage is 2.3 volts, and that is why the output rises faster with the input step. All right, let us look at positive, so +10 milli, and I'm again going back to 50 microseconds, and let us see what this does. Alright, so now the step is positive, so the output voltage will decrease, and for a 10 millivolt step, the linearized and the actual are basically the same, slight difference, it's okay. Let's make 20 millivolts. What happened now? For 20 millivolts, the gain is 100, so 100 times 20 is 2 volts. Alright, the output was, DC output was 1.5. It has to go down by 2 volts if the circuit remained linear, but 2 would mean minus 0.5. The output, of course, will not go below 0, so the output is saturating at 0.15 volts, because what has happened, the PMOS is still on, but the NMOS has gone into triode, and therefore the output voltage is very small. But the initial, when during the transient, the linear and the actual are more or less equal, because still the input voltage step is small. All right, so even for 20 millivolt step, the linear model is valid until the output kind of, well, until M1 goes into triode. All right, now let us do 200, which is a large step. So what was happening, we saw this 200 millivolt plus 200 millivolt step would turn the PMOS off immediately. So let's see what this does. All right, so now the red is the linearized, so that is rising. The actual, first of all, it is linear, and it is growing slowly than the linear predicted model, because now the rate of change of the output voltage is limited by the saturation drain current of the NMOS. This is the slewing limit. This circuit cannot cause the output voltage to decay any faster than what is given by this plot, because this is limited by the drain current of the NMOS transistor. All right, let me go back and do this negative step again, because it is important. So for a negative step, the slew rate, the dV or dt was higher than the linear predicted model, because as we saw, for a negative step, the rate of change depends on the PMOS drain current, and the PMOS drain current will keep on increasing as the magnitude of the step is increased. All right, this is what we'll discuss today. Let me see what I have. Yeah, okay, we discussed all of this. All right, so next lecture, we'll look at transients with sinusoidal inputs. This was step inputs. Next time it will be sinusoidal inputs.